right. Hello, everybody. Welcome to our continued discussion on probabilities. We have a little bit more to do, but not a lot. Not contents, yeah. So we've done most of the hard stuff for the probability portion. We just want to wrap things up, and it's really not that much. Uh, We might not take all of the session's time, but we have it, so let's continue. So what I want to do, actually, I'm just going to save time this time and just introduce everything by way of exercise 7.1 rather than introducing it and then changing things up with 7.1. Let's just do 7.1. It'll be the same. So let's read it. An experiment consists of rolling two dice and noting the largest number that appears. Now, let's just think about that before I continue, because as we're working our way through this exercise, through this example, we're going to elaborate on certain things. So whoa, the first things I write are always so weird. And it's fine. 7.1, we said. Okay, so we have an experiment, and it's now going to be important to be very aware of the action that we're doing to create results. And then there are probabilities associated with what could happen, of course, right? So in this case, it says we are rolling two dice. Roll two dice. Let's say we have one red one and one blue one. And then we write down the, or mix it up, the largest number that I see. Largest number that I see. So let's write down all possible outcomes. And this is why I say that it's very important to understand what we are doing, what we are writing down. I think of myself as a scientist in a white lab coat, and we're rolling these very two important dice. And every time it is done, I write down on my clipboard what the result is. So the wording is important. I'm not writing down, for example, I roll a 2 and a 3. I don't write down 2 and 3. I write down, as the result of this experiment, the largest number that I see. So, for example, if we roll 2 and 3, then the outcome of the experiment is 3, the largest of the numbers. So if I look at all possible outcomes that could occur, let's write them in increasing order. The smallest number that I could ever write on my clipboard is a 1. When I roll two ones, the largest of them will be a 1. I can also write a 2 on my clipboard by rolling a 2 and a 1 or a 2 and a 2. Both will result in the largest number being a 2. I can certainly have 3 as the largest number, 4, 5. I can get a 6 if I roll a 6 and a 2, for example. Let's say a couple examples here. Roll 6 and maybe a 2. Then the outcome that I'm interested in writing down as the result is the largest of the numbers. But because my two dice are just six-sided and fair balanced dice, I can't get more than a 6 ever. So the largest number will never be more than a 6. But I could, in another situation, still roll 2 dice, but be interested in something else. Maybe I'm interested in adding up the 2 numbers that I see. Maybe I'm interested in subtracting them. Maybe I'm interested in the smaller one. A, a lot of different things could occur from still rolling 2 dice. So it's now very important to understand what we're doing and what we're interested in observing as results of the experiment, as outcomes to the experiment. So here are the possible outcomes. So then I can now say another example. Not in continuing this. Let's call E the event that the largest number dice roll is, let's go with 2. Let's just make the first one easy. 2. Just check here if everything is running as it should. Seems to be okay. All right. Largest number is a 2. Let's say 2. Then I can, with my current knowledge and experience, write down the probability of this event occurring. Remember, this is now just conventional probabilities, no conditional stuff happening here. I count how many ways I can get it, divided by all possible ways. Now, counting isn't necessarily the same as the outcomes, as listing the outcomes. Because if I look at the list of possible outcomes, they are not all equally likely. Not all equally likely. If I just think about rolling some dice, getting a 1 as the largest number is going to happen not nearly as often as getting a 3 or a 4 or a 5 or a 6. Because I can only get the outcome 1 from rolling 2 1s. But I can get the outcome 4 from rolling a 1 and a 4, a 2 and a 4, a 4 and a 3, 2 4s, lots of different ways, right? So it's much more likely to get a 4 as the outcome than it is a 1. These are not all equally likely. So it's not 1 in 6, one of these outcomes over 6 possible outcomes. No, this only works if they're equally likely, if the things I'm counting are equally likely. So the more you think about it, the weirder this gets. And some people never think about it, which is also okay. But when I am trying to calculate probabilities, I need to conceptualize creating this outcome in a way where all the things I'm counting are equally likely. So now here I'm going to count the pairs, let's say here red and blue, because all possible pairs of numbers for these 2 dice, those are all equally likely. So when I look at how many different pairs I can get, there will be 36 possible without any restriction, because I have 6 possibilities for the first one, 6 possibilities for the second one. I multiply these, or you can think of a tree, 6 possibilities for the first roll, and then for each one, it branches off into another 6 for the second roll. So I have 6 times 6, 36. Now, for our purposes, it's not going to get much worse than this at all. Now I'm looking for the number of pairs that would give me the event E. And the event E is the largest number, is a 2. So here I'm just going to list them. I can get a 1 and a 2. That would result in the outcome 2. A 2 and a 1, or a 2 and a 2. Those are the only possibilities, and I get 3. So often with dice rolls, I can just list them. I can't list 36 of them. I guess I could, but I don't want to. But when I have a restriction, I just list all the possibilities that I can see instead of trying to come up with something fancy for our level. Okay, so I get 3 out of 36. Then I can go and say the same thing for all the others. I can define a new letter for the event that the largest number is a 3. I can do the same thing and I'll get a fraction. But it's a little bit inefficient. There's nothing wrong with it, and I certainly want to now see, well, okay, I only have 6 possible outcomes. What are the probabilities associated with each one? So let's say, let's not write it there. Let's do it like this. So we're not going to do anything different really. We're just going to streamline things a little bit. Because the outcomes of this experiment, the outcomes are numbers 1 to 6. And when I think about numbers, variables are not far behind. So just to streamline the naming of this event, we're going to say, let's pick a variable, and usually an x or a capital X or y or something like that. Let x represent the uh, outcome of the experiment. Now, different experiment, different explanation. Of course, I have to put in the words here. In this case, the largest number from rolling 2 dice. But it's always the outcome of the experiment, even though the experiment could change. Then the possible values of x are 1, 2, 3, 4, 5, and 6. We're not doing anything different, really. We're just giving it a different look, if you will. See how we're doing the same thing. We write the experiment, we understand what we're looking for, all possible outcomes. Now I'm just associating these values, these outcome values, with a variable. So then if I look at my event E, now instead of defining new letters for new events and listing them all, we can, for example, write event E as x equal to 2. This now means the same thing. It's just a different way, it's a more streamlined, efficient way to talk about the outcomes. I don't have to redefine a new event if I want to talk about the outcome of 3. I'm just looking at the value of x being 3. I need to define a new event if I want to look at getting the largest number to be 5. No, I could just say I'm looking at x equal to 5. So it's just a little bit more efficient. So I don't have to redefine a whole bunch of events. For 6, it might be okay. What if I have 10 possible outcomes? What if I have 100? Then with a single variable name, I can represent a variety of events. It's just efficiency. So for example, here I could say the event, that's ugly, not doing anything new, just trying to be more efficient. The event that the largest number is at least 3, that can be represented by x greater than or equal to 3. I don't have to define new letters, new events. I can phrase them using a single variable. Okay. So now this variable x, though you can rename it, in this case x, has more than one possible value, right? In this case 6. And there are of course probabilities associated with each value that X could have, because those values represent all the outcomes. We saw one of them. This one is going to be the probability that X equals 2. And for each value of X, I'm considering each outcome, and there's a probability associated with each of those. So we call X a random variable. It's a very unfortunate name. It is not the original name. The original name is a stochastic variable. A stochastic process is one where I don't know the outcome. It could be one of a few, and there are probabilities associated with what could happen. Random gives it a bad image. Random feels like, oh, anything can happen. It's random. No, it's not random, actually. Only the numbers 1 to 6 can happen, and with specific likelihoods as well. It's not really random. But somewhere someone decided, oh, stochastic, that's a scary word. We can't use that. People won't buy our books. So let's make it the word random, even though that's not really what it is. It's not random at all, actually. So random variable is what everyone uses these days. So now we have this random variable simply for convenience. The convenience is to refer to and represent a variety of events around this specific experiment. So let's look at all the probabilities. So now we want the probability that X equals 1. Now I'm going to look at it in the same way as we did our initial one, which we've already seen, right? We've already seen this one was 3 out of 36 because it was exactly the same as the event E. But instead of defining new events, I just refer to different values of X. So now I have to understand what I'm reading here. X equal to 1 is just the name of an event. What is the event? The event that the largest number is a 1. How many ways can I get that? By rolling 2 ones. There's only one way. Let's go over here. Probability that X equals 3. We're going to do them all. X equals 4. Maybe over here, X equals 5. And maybe over here, X equal to 6. Those are then all the possible values of X, all the possible outcomes to the experiment. They're all going to be over the same sample space because I'm counting all the possible pairs. Now, X equal to 3 means, in words, that my largest number should be a 3. 1, 3, and 3, 1. 3, and 3, 2, and then 3, 3. So there are only 5 of them. If I go to 4, that means the largest number should be 4. The only purpose of the random variable is for conveniently naming events. People think, oh no, this is so much worse. It's so complicated. It's not. I'll say again, the only purpose for us, for a random variable, is to conveniently name events. Nothing else. So now X equal to 4 represents the event that the largest number is a 4. How can I get that? By counting pairs, because I need to count equally likely things. 1, 4 or 4, 1 would give me a 4. 2, 4 or 4, 2. And you see, just listing them is not hard. We won't do it for all of them once you see the pattern. So there's one exception for the double, and the others can be swapped to give me 7. When the largest number is a 5, we hopefully see a pattern here, and it is indeed going to be 9 out of 36. Largest number going to be a 6. excuse me, it's indeed going to be 11 out of 36. Okay. So we've saved a little bit by not having to define different letters for all these different events, and they're all different. And we have the bonus if we want to get fancier with different kinds of events by grouping possible outcomes, we can still use our random variable just by way of an inequality. Okay, it's good. So now, for example, I forgot to look at what we're actually doing. I just used this setting to do everything we need. List all the possible values of x. Check, we did that. Determine the probabilities associated with all the different values of x. Check, we did that. Now, before we get to the next bit, I want to just note, for example, we can combine these. If I look for the probability that x equals 1 union x equals 6, that looks bad, perhaps. Maybe brackets are nicer. Doesn't really matter. Remember, this is just names for events, and events are just sets. And I can merge the requirements of those events. It's the probability that x equal to 1 plus the probability that x equal to 6. Technically, these are events, right? These are sets, rather. So my formula says the union is the sum of the individual ones minus the intersection, but these have no intersection. They're completely, we call them mutually exclusive events. They have no overlap, so I just add them individually. So people are bothered by the fact that there are equal signs inside these and all over the place. No, they're just names, really. So then I'm simply going to add up 1 over 36 plus 11 over 36 and get 12 over 36 as the chance of getting the largest number to be a 1 or a 6. Because there's no overlap between these. I can't both get the largest number to be a 1 and be a 6. I just add them up separately. Just like we add up different paths that have no overlap. Okay, so that's a side note. So now it's nice to just do all these probabilities, but if there are more of these in a different experiment, then this is a little bit unstructured. So all we want to do is summarize this in a table form. So now how can I structure my table? I can do it as a row or a column. It really doesn't matter. I'm going to do a column. So now I want my heading to be the probability that x equals a number. And that number is going to range from 1, 2, 3, 4, 5, and 6. Those are all the possible values that x could have. So I use a little n for convenient table column headers. So then we already saw the probability that x equals 1 is 1 over 36. I did not leave myself enough space because these are fractions and they need a little bit more space. Ah, hindsight. There we go. Probability that x equals 2 is the event that the largest number is a 2. We have already done it. We're just summarizing it in table form. And we can just copy them all. Barely have space for these. There we go. Yeah, it's exactly the same thing. And actually the table, I think, is way nicer. Easier to read. Everything is just nicer. Just be comfortable with using this n for the different values, right? Let's observe something. Observe. If I add up all of these, whoops, add up all the probabilities, these guys. I add them all up, I get 1 out of 36, that's 4, that's 9, that is 16, that is 25, 36. 36 out of 36, or 1, or 100%. Does that make sense? Yes, because this is anything that could happen is in this list. Nothing that is not in this list can ever happen. I'm gonna get one of these results. So if I pool them all together, there is a 100% chance of getting one of these because I've listed all of it. So I have to always list everything. And I can use as a check, if I need to find these probabilities, I can check by adding them up, do they add up to 1? Now, it's not a guarantee that if they do, I'm correct, but if they don't add up to 1, I did something wrong for sure. It could be that one of these probabilities is wrong. It could be that I didn't list everything, but at least I have a little bit of a check. Save here, use as a safe, what is that? What is that letter? In F, safety check. I can definitely use that. Okay. Alrighty, let's go back and just double check. Represent the probability distribution as a table, graph, formula. Okay, we're not going to do formula because we don't need it. It's coming from an older version where I did way more counting and then formulas are kind of necessary. Let's graph it. So before I do that, this whole thing, as well as the top here, as well as this, where I list all the probabilities. This is called the probability distribution of X. I have to say the variable. The variable in question is linked to here. The variable is linked to the experiment. It is the outcome of the experiment. The experiment is a specific thing that I'm doing and observing as results. The random variable is essentially the representative of this experiment and kind and type of outcome. If I still roll 2 dice, but I add up the numbers instead of writing the largest one, different random variable, different experiment outcome combination. It'll have different probabilities. It'll be the probability distribution of that random variable, of that experiment outcome combination. Why probability distribution? Well, they are probabilities, and this table shows how the probabilities, 100%, are distributed across the possible outcomes. Okay, probability distribution. Now, table form is nice. Definitely go with that. But if you want something more visual, we can certainly go with a graph. And we will go with our basic bar graph. I should use the straight line tool, I know. But when, loosely speaking, when we are representing probabilities, we don't call it a bar graph, we call it a histogram, blah, blah, blah. Doesn't really matter, right? I have the numbers, the possible outcomes of X here. 1, 2, 3, 4, 5, and 6. Now, for technical reasons I don't really want to get into, I don't really care that much. Technically, histogram doesn't has the bars touching each other. But for our purposes, it's all just aesthetics, really. So I picked my first height, which was 1 over 36, right? So it's going to be a little bar like so. Again, if you want to position it differently, you want to just make it uh, a single dot there. There are different variations of this, and they all represent the same thing. Then at 2, I have a bar that has height. The key thing is that however you draw this bar, whether it's a thin, tiny little bar or a thicker bar, it has to have height matching the probabilities, these probabilities. Okay. Then I'll have a bar a little higher at 5 over 36 that sits at 3, and so on, right? Just giving me a more visual summary. In this case, they all just go up and up and up based on the experiment that we have. I'm not going to write them all in because they are squished together. The last one is 11 over 36. But for a different experiment, and through the problems and everything, we'll do different ones. You'll get different shapes here. But visually, it's nice to see just how they are related. It's just an alternative. Again, we're not going to worry about formulas. It serves no purpose for us. We didn't do our counting to that level of detail that can justify worrying about formulas right now, so I'll never ask it. Don't ever worry about it. And the two main properties of the probability distribution. Well, we listed one. This was one property, that it adds up to 1 or 100%. And the other property is, I guess, kind of obvious. We don't really think about it. These are all probabilities, which means they're all between 0 and 1, between 0 and 1, between 0 and 1, because they're all probabilities. So I'm not going to write that one down. It's never really an issue for our level of difficulty. Okay, so that introduces all the concepts surrounding, well, almost all, surrounding probability distributions. I'm going to introduce the last one when we do uh, the exercise 7.2. And we're only going to do these two. And if we don't get to them all, we'll just continue tomorrow. Tomorrow's a little empty as it is. Alrighty. Okay. Just check if everything is still looking good. All right. So let's get a little bit more practical. Rolling dice, it says here in the book, rolling dice is all good and well, but sort of academic exercises, really. So let's look at something like 7.2. For a weekly raffle, 1,000 tickets are sold at $2 each. Can we see the top here? I didn't cut it off. No, it's good. Okay. $2 each. There is one first prize of $100, two second prizes of $50 each, and 7 third prizes of $20 each. Determine the probability distribution associated with your net winnings or your profit if you buy one ticket, one random ticket. Okay. So now I strongly encourage you, even though they do not ask that directly, and another question might, always, always, always clarify to yourself what is the experiment, what do I consider to be an outcome, what is the random variable. Because the random variable matches the experiment and outcome combination, I'll say. So the experiment is buy one random ticket, which means all tickets are equally likely, random. What is an outcome? An outcome is my profit, or what they call the net winnings from buying one ticket. So now I say let X represent the profit from buying, one random ticket. See how the random variable is the experiment outcome combination. They are connected. If the experiment changes, like I buy 2 tickets or something, or the outcome changes, like whatever else it could be, maybe not profit, but just winnings, then the random variable has to change as well. They are tied to each other. But in this case, they're talking about profit, so I define my random variable as x accordingly. Once I have that, the possible values of this random variable is what I am listing. Okay. I'm always going to do this. Always going to do this. Now, when you get more comfortable, you can do this experiment outcome to yourself in words because those words feature in the random variable sentence anyway. So you don't have to double dip, but it's always nice, especially in the beginning. So the possible values of my random variable. Now understanding that it represents the profit, let's go back to the question and see. Well, what's my best case scenario here? I can win $100, but it costs me 2. So my profit is 98, and X represents the profit many times, many times. Maybe it's happening right now. People want to write 100, and it's because we just need to take the time and understand what an outcome is in this case, what the random variable represents in this case. It is the profit. So you cannot say 100. That is a different random variable, not the one they want. So it's 98, and that represents winning first prize. But remember, that's just a name, right? A name for a result, a name for an outcome. I have a second prize as well. It's going to give me $50, but I pay $2, so 48. So when x equals 48, it's just a name for the event that I win second prize. Make that association as early as you can. And then I can also win third prize, $20. Nice, it's not bad. 18 profit, I'll take it. Now many people stop here, but there is something else, unfortunately, that could happen, whether they explicitly say it or not. Obviously, there are only 1 plus 2 is 3 plus 7 is 10. There are only 10 tickets that will give me a prize, and there are many other tickets that will be losing tickets. So, unfortunately, as much as we don't want to, we could lose. And then our profit is -2. We have to list all the possible values of x because those are all the outcomes of the experiment. So -2 represents we lose. Next, the probability distribution. Probability distribution of x. And table form is very nice for us, so we'll do that most of the time. If they really want me to graph it, they're going to have to ask me because it's going to take me longer, but you are welcome to practice it. So I'm going to do it in column form, and it'll always look like this. Different values of x, 98, 48, 18, and then -2. Now, I already have a situation where the tickets are equally likely to be selected. So I have a possible 1,000 tickets I could buy one from. There is one specific first prize ticket. So my chances of winning first prize is 1 in 1,000. So see, our probabilities are nice and simple. And you might have a good intuition about them as well. 1 in 1,000. Of course it is. Shift this over because, of course, I didn't give myself a lot of space. When I talk about x equal to 48, I am just talking about winning second prize. I think there were two. There were two second prizes. So if I buy any one of those two tickets, I'm winning second prize. X equal to 18 represents winning third prize. Out of 1,000 tickets, I'm going to have to buy one of the 7. That would give me that. And then I see, well, I have accounted for 10 winning tickets. So there are, out of the 1,000, 990 losing tickets. Now we can calculate these. You can write the decimal versions. You can write percentages. It's correct in all cases, regardless of how you want to refer to the probability. Doesn't quite give me a good indication of what is happening in this situation. Even if I graph it, I could do a very rough graph here, right? I'm going to have to put -2 over here, and then they're all sitting, maybe 18 is over there, 48, and 98. So I have a very teeny tiny, I'll just do little bars like this, very teeny tiny 98, and a slightly higher 48, and a slightly higher 18, and then boom, very likely in comparison, -2. Still doesn't quite capture something that I can quickly use to analyze this situation. Is it profitable for me? Just because I'm losing with a high probability doesn't mean this might not be a good game to play, because the value of the prizes are factors into that decision as well. If the prize is value is much more valuable than the ticket price, well, yeah, I have a small chance of winning it, but if I do win, then it's totally worth it, right? I could play a little bit, risk my money because it'll be worth it. So I can't get a good intuition of whether this is a good game for me to play or not. I need a number. I need a way to associate a number with that assessment of this situation. In steps the expected value. Expected value. It's going to be a number, I'll say here, of x. It has to be associated, of course. It's a way to summarize the probability distribution by way of a single number. We call it a measure. A measure is simply a single number that captures sort of the overall information. We're going to call it E for expected value, and then in square brackets, I have to refer to the random variable in question, because that random variable is what is representing the experiment outcome, everything about what I'm doing. It's all captured in this X. So that's how I'm going to name the expected value. So it's a very simple calculation, and I'm not going to go into why at this stage, at least. All I'm going to do is I'm going to go down this list in my table, take each of the values and multiply it with its corresponding probability. And then I'm going to take the next one and multiply it with its corresponding probability or associated probability. Then I'll take the next one and I'll go down the line until they're all done. Remember, this one is -2, and I multiply that with its corresponding probability. And of course, now it's a calculation, so I'm going to get a number. Let's calculate it. Let's show it in the chat. I know I'm at my time, but we're so close. We'll do the next exercise first thing next time. Then let's just calculate this. So I have 98 times 1 over 1,000 plus 48 times 2 over 1,000 plus 18 times 7 over 1,000. Technically, this one is minus 2 times 990 over 1,000. Did a bunch of hundreds. Hold on. Fix that. And I get negative 1.66. Now this number can tell me a whole bunch. If I look at the range from -2 to 98 of possible values of x, the expected value can tell me, can be interpreted in two ways, and I have to finish it. It sits right next to this, -2. The probabilities pull it in different directions, higher probabilities, and that value, that outcome has more weight in this calculation, and it pulls the expected value to that. It's a kind of an average, summarizing all the information. Because it's closer to this -2, it gives me an indication that of what is more likely to happen. Okay. But there's a more important. So this is sort of a long-term average, this expected value. And I can interpret it that way. So we have to write it out, and then we'll repeat that next time with the following example. This expected value tells me the following. If we repeated this experiment, in this case, play the raffle game, experiment, many, many times, I'm going to do it in general. The average of all x values, remember that's the outcomes, will get closer to this expected value. This is now in general. I can now apply that interpretation to my specific situation. That means if I played the raffle over and over and over and over and over, many, many, many times, the more I play, the more my average profit will be negative 1.66, which means I will lose, specific to my example, the more we play, the closer our profit. Oh, I cannot write clearly because I'm in a hurry. I should just slow down. The closer our profit will be to negative 166, which means we will lose $1.66 per game on average. So that tells me a whole bunch. It tells me that if I play this raffle and I win, let's just suppose I'm super lucky and I win one of the prizes. Should I keep playing? No, because you will slowly lose on average $1.66 of those winnings until you have nothing left. It shows you where the balance, where the balance point, if you will, of this game sits. It's in the negative, which means long term, this is a losing game for me. Now, another game could have a much higher prize or much higher prize values and then give me a positive expected value. So if I play enough, I'll make a profit. And then I have to decide, well, is it big enough for me to risk it? There's still risk, right? And I can make a more informed decision off of this single measure, this expected value. Now, if you're not perfectly comfortable with this, we have a follow-up exercise, example 7.3. you're welcome to try this if you want to, or you can just wait and we will do pretty much the same kind of thing just to emphasize this next time. But we have to unfortunately pause there. I keep going over the time, but I need to finish this. Right? Are there any questions or thoughts on this? All right. Then we will pick this up with the next exercise, the next session. Until then.